For magnesium, it's 44.7 gigapascals. And for this specific alloy of steel, 193 gigapascals. Because there's a thermal component to this, we're also going to need for both of the materials their coefficient of thermal expansion. For the magnesium, it's 26 times 10 to the negative 6 per degree Celsius. And for this alloy of steel, it's 17 times 10 to the negative 6 per degree Celsius. These are really like, what are we in, metric, millimeters per millimeter per degree Celsius. This is a strain measurement per degree Celsius. Since we're going to be using PL over EA, it's also going to be helpful if we write down now the original lengths of our materials. The magnesium core on the top is bound by that rigid plate, on the bottom by another rigid plate. The magnesium is originally 0.1 meters. However, each steel bolt, the steel bolt goes through the rigid plate. The steel bolts are originally longer, 0.15 meters originally. Our base temperature, 15 degrees Celsius. Okay, so that's enough for now for what we were given. And we will find T2. So what temperature can we raise this system to before either the magnesium or the steel has 12 megapascals of stress in it? Right, for this type of system, how many free body diagrams, just by inspection, will we need to be able to solve this? Right, in this one, they're in parallel. So if we make a horizontal cut, it's going to be one cut that goes through, and keep everything above it, say. It's one cut that goes through both of our materials. Now we have a steel on the left and a steel on the right, but we can argue through symmetry they're going to behave exactly the same. And this is where we have a choice to make, similar to the third quiz, I believe, of how do we treat the steel. Right, so we make our cut. There's no external applied forces. All of the stress is coming from the thermal effect. We're cutting through the magnesium, so we can see the internal load in the magnesium. This is where we now have a choice. We can either treat the steel bolts individually, however, through symmetry, assume that they're behaving the same, or treat the steel as one collective material. What this is going to affect is if we treat it as one collective material, we have one force that's the force in all of the steel. But then the area is the total cross-sectional area of the steel that we're talking about. Or we treat the steel individually, which is how I did in my notes. But now the cross-sectional area changes because now it's only the cross-sectional area of an individual bolt. The end result will be the same because either I'm doubling the force and also having the area, or I'm doubling the area, but I'm only having one force I'm talking about. So the end result is the same as long as it's symmetric. So in the one free body diagram, we have, I'm treating each steel rod independently, and I have the force in the magnesium. So this will be reflected by some forces in the y direction. Will be negative 2p steel minus the force in the magnesium. And I'll rearrange it now since I know I'll need it later to make that substitution. It means that the force in the magnesium is equal to negative 2 times the force in the steel. In this case, because of the way they're bonded together, however much one expands, the other one has to expand the same amount. And since we're heating it, we expect it to be expanding in general. So because they're bonded together here, if the magnesium is pushing out these rigid plates, however much that delta is, the bolts also have to expand that same amount, assuming that these are rigid plates and they're going to stay horizontal through that expansion process. So the compatibility, the change in length of the magnesium is equal to the change in length of the steel. They do have different original lengths, which will be reflected in our equations, but however much they deform has to be equal to each other. I'm treating the steel pieces identically, so if I know the change in length of the left bolt, it's also the change in length of the right bolt. So I can compute the deformation of the steel. Will be P steel times the original length of the steel is 0.15 over the Young's modulus of the steel, 193 billion, times the cross-sectional area, which I did not compute out, but it's going to be pi over 4, times their diameter of the stainless steel bolts is 10 millimeters. There's a thermal effect here, so I have to add alpha delta T times L. For the steel, I have 17 micro as my alpha. The original length of the steel, again, 0.15. And for right now, I'm just going to call it delta T. At the end, I'll figure out what T2 is. I could say it's T2 minus T1. I think this is easier to start. It's a little bit easier on the algebra at this step. So that change in temperature. And so you have numbers to look at for this. This is going to be 9.9 times 10 to the negative 9 times P steel plus 2.55 times 10 to the negative 6 delta T. Magnesium, same idea here. PL over EA, but we have a different A, E, and L, times alpha delta TL. Alpha is different. I'll skip the intermediary steps. This simplifies to 1.14 times 10 to the negative 9 P magnesium plus 2.6 times 10 to the negative 6 delta T. I have 4 equations right now, but I have 1, 2, 3, 4, 5, here it is, delta T unknowns. So this is a case where we got to the end of the DIL steps and we don't have enough equations to solve for all of our unknowns. We have a relationship here between the force in the magnesium, force in the steel, but we can't at this point get numerical answers for everything that we do. So we do actually have to add those stress equations. This will be a little bit trickier compared to some of the other ones. But we need that 5th equation to get that 5th, to solve for that 5th variable. All right, so this one's a little bit different here because we don't want the stress in either the magnesium or the steel to exceed the 12 megapascals. So when this thing is expanding, the magnesium wants to expand more than the steel, which means that probably the steel is going to be stretched more than it wants to, and the magnesium is going to be compressed more than it wants to. We want to keep that in mind when calculating this, because if we know the steel is going to be in tension, we should get a positive value for its stress. And that will make a difference in our calculations. So for the steel piece, we expect it to be in tension. I'm setting P over A equal to positive 12 million for the 12 megapascals. I won't go through the algebra steps, but if we look at equation 5a, 1, 2, 3, and 4, we now have 5 equations for 5 unknowns. So we can solve for delta T when we're using these 5 equations. So for the steel to have 12 megapascals of stress, that delta T is going to have to be 229, positive 229 degrees Celsius. But what we also need to know is what would it take for the magnesium to go to 12 megapascals. But here's the difference. When we're raising the temperature, again, the steel is in tension, the magnesium is in compression. for that to hold true, I have to make sure that I set this equal to negative 12 megapascal. P magnesium over A magnesium. So in the second scenario, I'm raising the temperature until the magnesium has 12 megapascals of stress. I'm now using equations 1 through 4 and 5b for this scenario. So ignore A for the moment. What temperature causes magnesium to have a compressive stress of 12 megapascals? That happens if we raise the temperature we have to raise the temperature by 2,870 degrees for the magnesium to have 12 megapascals of stress in it. Right, so we are looking for the lowest temperature or the lower temperature. So the delta T that will cause the first one to have 12 megapascals of stress is the 229 Celsius. So if we add to our original temperature of T1 is 15, we get that if we raise the temperature to 244 C, the steel will just have 12 megapascals of stress.